This video is about the paper called Part-Dependent Label Noise towards Instance-Dependent Label Noise. This is a paper that was published in NeurIPS of 2020 and is concerned mainly with the problem of dealing with instance-dependent label noise. The difference between instance-dependent label noise and general symmetric or asymmetric label noise, or class-wise symmetric or asymmetric label noise, is that in the instance-dependent label noise, the semantic content also play a role in how the noise is applied. In other words, there is this assumption that the semantic context of the image can contribute to a pattern in the noise that can be learned. They mentioned that there are psychological and physiological evidences that humans perceive instances by decomposing these instances into parts, which therefore renders the human annotators to make mistakes based on parts rather than the whole instances. To address this specific problem, they propose the part-dependent label noise as a way of approximating this instance-dependent label noises. Basically, they mentioned that if you consider the transition matrix, you can construct that transition matrix, which indicates to what extent one label can be mislabeled as another, by a combination of part-dependent transition matrices. And then they combine these into creating the transition matrix. And empirically, they show that this approach is superior to the state-of-the-art approaches when it comes to learning instance-dependent noise. In starting the discussion of their work, they mentioned that the works that deal with label noise can be, roughly speaking, divided into two categories. Category 1 is model-free, and the category 2 is model-based algorithms. In the first model-free category, there are heuristics that are used to reduce the side effects of label noise without actually explicitly modeling them. For instance, extracting confident examples or partitioning based on loss. They mentioned that without actually explicitly modeling the label noise, the reliability of such approaches cannot be guaranteed, and they mentioned that, for example, methods that are focused on small loss items in the dataset do have the underlying assumption of accurate label noise rate in order to be really efficient. Then they go about the definition of transition matrix, which is a matrix-valued function, and its objective is to explicitly model the generation process of this label noise. This means that when you have the item X, when you pass it through this transition matrix, which is a matrix-valued function, you will get T matrix of Tx, which the element ij indicates that if the real label is I, and the observation is X, meaning that you somehow incorporate the semantic context of the item, what is the probability of observing a label J, which could be a noisy label, that is not equal to I? The basic idea of using this transition matrix is this idea that clean class posterior can be inferred by using the noisy class posterior when you have the transition matrix. Using only the noisy data, it is not straightforward to learn these transition matrices. Therefore, they mentioned that in the literature, some simplifying assumptions have been common to make the problem more straightforward, such as having access to additional information, having a symmetry assumption for the matrix, having upper bounds for the noise rates for instances, or even to be instance independent. It is mentioned that in practice, such assumptions are hard to verify. In the approach proposed in this article, the assumption is that the noise for an instance depends only on its parts, which is a kind of noise they define as part-dependent. The motivation of it comes from the fact that human annotators usually annotate the instances based on the observed parts rather than the whole instance, and they want to use the semantic information of these parts to make it work. They mentioned that such transition matrices for these parts can be learned by using anchor points. And they define anchor point as instances that belong to a specific clean class with probability 1. In using this article in practice, they mentioned that in some cases, for instance, in the cases of heavy instance-dependent label noise, for example 50%, using this method leads to advantages of almost 10% of test accuracy on CIFAR 10 dataset, which suggests that it has significant advantages. In the discussion of related works, they go over the different types of label noise, which are random classification noise, basically random flipping of labels, class conditional label noise, meaning that the noise depends on the classes, and therefore you will have a general transition matrix that basically defines how these different classes can go to another, but it is still not dependent on the semantic content of the specific instance. And finally, the instance-dependent label noise, or IDN. Given that the problem of finding out the IDN without any additional assumption is hard, They proposed this part-dependent label noise, and they mentioned that it is somewhere between the class conditional noise and instance-dependent noise. Let's say S bar, which is a set of xi, yi tuples, be the dataset or the training dataset, which does contain instance-dependent noise. Now consider a data matrix X, which is composed of these representation vectors. One thing to note is that these could be observations themselves or could be representations learned by a deep neural network, for instance, which was pre-trained or which was trained on the noisy training set. They formulate the part-based representation learning for this part-dependent label noise as follows. Let's say you have a vector representation for instance I, and let's say you have the parts of instance that is in a way that each column of W indicates a part of Xi. And let's say for the item Xi, you could pass it to a function edge, and you get basically the combinations to reconstruct Xi, which is going to be a vector. Note that these have the same dimension, this doesn't. Thus, considering the items 1 to n, you can have this objective, meaning xi minus w times hxi. Note that this would signify the certain coefficients and basically would have a weighted average of the columns of w, for instance, I. Now we take the square value of its L2 norm, and you want to minimize this subject to certain constraints. One is that w is going to be of real valued numbers, and this combination has to be positive, and also it has to have a norm of 1 because you are using it as the way to essentially decompose. And this has to apply for all of instances. The idea now is this. They assume that there is a part-dependent transition matrix. For example, for each one of the parts, you are going to have a matrix with values between 0 and 1 from the dimension C to C, which basically is the number of classes. And they mentioned that given that you have R parts, you basically would have R different part-dependent transition matrices, or PJs, from J to 1 till R. And the idea is that parts can be used to reconstruct instances, and they exploit the idea that instance-dependent transition matrix can be approximated by a combination of part-dependent transition matrices. One assumption they have here is that once you have the parts in the semantic space, they have this assumption that the parameters for reconstructing the instance-dependent transition matrix are identical for those that are used to reconstruct the instance representation. And the intuition behind that is that these learned parts, you are using the semantic context, therefore the same composition of the actual observation has to hold for the part label noise as well. Thus, knowing that for each one of the j's from 1 to r, and basically r is the number of parts, you have a transition matrix which is specific to that part, you will have basically the components associated with the instance, and you tune the weights and you take the weighted average of all of these part-based transition matrices, and you create the instance-dependent transition matrix by that. Now let's discuss learning these part-dependent transition matrices. For the class I, let's say xi is an anchor point. This means that the probability of this label for this item being I, given that this observation is xi, is 1. Now for this anchor point also, you can write that probability of the noisy label being j, given that x is equal to xi. You can write it like this based on the C classes that exist. Namely, you can consider a noisy label j that was given, you could consider a real label k, and of course the observation is xi, and then you would also have this based on chain rule. Now let's look at this more clearly. You know that given that xi is an anchor point for the class I, for any k that is not equal to I, you will have this probability to be 0. And in the case of k equal to I, you will have this probability to be 1. Therefore, what you will have is this. You will have the probability of the noisy label being j, given that real label is k and instance is xi, which if you remember, it will be the elements ij of the transition matrix that of the instance-dependent transition matrix associated with xi. Now, let's go back to this equation. We had that for an instance x, you would have this approximation of the transition matrix by this. So you would have r parts, and then you would have hjx, and you multiply this by a transition matrix. Now, let's say you have an anchor point for class I, and this means that you can essentially approximate the row, basically the ith row of the transition matrix for x. So you have an item x, and then you have hjxi, and you want to learn the transition matrix, the ith row of the transition matrices from J1 to R. This means that for R parts, you need R anchor points in order to be able to solve this problem. Now let's say you have R parts, and let's say you have anchors for class I to be, let's say you have K anchors for class I. They propose to take the ith row minus this construction of the ith row of this probability, and again you would take the norm of the difference between these two, and you have K anchor points and C classes, and then you want to pick the part transition probabilities that would minimize this whole thing. The algorithm for part-dependent matrix learning is also shown here. So you have a noisy training sample and you have a noisy validation data. Step 1 is to train a deep model by using the noisy data and the noisy validation data. Step 2 is to get the deep representations. Step 3 is to minimize equation 1 and use that to learn the parts and parameters. And then 4 is to learn the rows of this instance-dependent transition matrix by using anchor points according to the last equation, and then minimizing the objective function in equation 4 of this paper to learn the part-dependent transition matrices, which eventually leads to having the instance-dependent transition matrix for each instance. Let's go over the experimental setup in this paper. They have FMNIST, they have SVHN, CIFAR10 news. They have the clothing 1M, which is a real-world noisy dataset. And they use the pre-trained word embeddings from GLOV for news. They compare with cross-entropy, with the case where you train two networks on samples whose the prediction from one of them is different from the other. They have mentor-net co-teaching, co-teaching plus, and some other approaches. They also have approaches related to class-dependent transition matrix for comparison. They have been using NVIDIA Tesla V100, a ResNet 18 architecture for MNIST, ResNet 34 for SVHN and CIFAR10. And here are some more details regarding their optimization steps. They used the ResNet 50 for clothing 1M, which was pre-trained on ImageNet. And they also mentioned that the codes are available here. One other thing to mention is about the process of generating this instance-dependent noise. It is shown in algorithm 2 here. One thing that they mention is that it is straightforward to assume, and more realistic to assume, that the noise rates and flip rates depend on the instance-specific semantics. Now, what they have is a noise rate, and they have the clean data set. Let's say, for example, CIFAR10. What they do is that they sample n, means basically 1 for each example, which is going to be the flip rate. And they sample it from the truncated normal distribution of n tau 0.1 to the power of 2 and between 0 and 1. Then they also independently sample a vector for each one of the classes from the standard normal distribution. Now for each one of the items, what they do is this. Let's say item I has a real label yi. They have this w here. Now they want to generate a flip rate, therefore they consider xi and wi. This is going to be the probabilities for xi based on the vectors associated with yi. Now they also control the diagonal entries for this matrix by setting this to -infinity so that you don't have the flip to itself possibility. Then you perform softmax on it and you multiply the result by qi, which is going to be the sum of the off-diagonal entries is going to be qi, and then you basically put 1 minus qi on the diagonal elements, and then you choose a label from label space according to this probability, and you enter in this routine. Let's look at the case of FMNIST with different label noise levels. You have 10%, 20, 30, 40, and 50% instance-dependent noise. Now you can see that the best approaches are basically those that are focusing on part-dependent noise. Now this R and F here indicates the revision of the transition matrices by revate or forward algorithms. And we can see that the result on FMNIST was actually suggesting that the PTD approach is useful. The same goes for SVHN and CIFAR 10.